Okay, hey, okay, good. Okay. N plus, okay. KTH, okay. Kistler, excellent. And Move Solutions. Okay, great. We have almost everyone.
Okay.
Good.
Full program.
Full program, yeah. Okay, we should start. Okay, hello everyone. Welcome to SHM in Action, the signature event of this conference that is attracting this year 16 participants. And I'm glad to chair this session with
Marcel Bos.
Yeah, so Marcel is first time co-chairing the session. Christian could not make it this time, so I kind of inherited a little bit this as a co-chair. So it's great to have like new people also, co-chairing.
I look forward to 2 hours of chaos.
Okay, thanks. So we have 16 presenters. We have 2 hours if we want to get to the dinner, which means every presenter has 5 minutes, and we will measure the time. And we start with Politecnico di Torino, Turin Polytechnic, and podium is yours.
Thank you. Good afternoon, everybody. I'm Marco Esposito from Politecnico di Torino, and I will show you some of the future of the software that is called DEMOS, displacement monitoring using strain sensors. Okay, what is shape? DEMOS is a shape sensing software. What is shape sensing? Shape sensing is a technique that, starting from easy measurable strain data, can reconstruct the full displacement and strain and stress field of a structure. And DEMOS, our software, does that using the inverse finite element method. That is a method based on a finite element discretization of the structure. Of course, displacement and stresses are crucial ingredients to achieve a structural monitoring framework can be used as a feedback for morphing structure, for the orientation of a telescope, and for the realization of a digital twin. So which are the main features of our software? The first one is compatibility. We thought that since people that already use finite element software should use our software, you can build the finite element model using the usual software like Patran or Abacus. The second feature is the integration. We think of the software as an integrated solution in the sense that it can not only perform the shape sensing, but it can be used to design the monitoring system in terms of sensor optimization, strain sensor optimization, and also virtual sensor expansion in case you have few sensors. Last but not least, it's really important for us the accuracy of the displacement reconstruction and the efficiency in order to reach real-time remote monitoring. And we can do that thanks to the SSB-IFEM, that is the algorithm that is at the base of the software, and thanks to Wi-Fi connectivity. So the demonstration will only focus on the real-time remote monitoring feature of the software because I have only 5 minutes. And so since I could not bring a structure here in Stanford, we have a structure, actually a wing of an aero model in Torino, back in Italy, and I have my software here on my laptop here in Stanford, and we will try to do some really remote real-time monitoring. So I will connect with Professor Gerlone that is in the lab in Torino. You can see the real structure that is sensorized with strain sensor. Can you please arm the system and confirm? Professor, can you please arm and confirm? Okay. So this is the software user interface. You can see the FA model of the structure and also the sensing configuration. And I will start. Okay, can you start the test? Okay. So you can see the digital model and the real model. Now you can apply a load to the structure, please. Okay. So you can see that we are in real time from Torino. And you can see also here we have a strain concentration there that we are able to detect because Professor Gelloni is actually loading the wing in a section where there are no more spars. So there is a decrease in the stiffness and so a stress concentration. If you can move the load closer, oh, sorry, it's not listening to me. If you can move the load closer to the root, you can see that the stress concentration disappeared, okay? And we have a stress concentration at the root where we expect it to be, okay? And we also have some warning. I don't know if you saw some warning. Can you please activate some warning with a big load? You can see that we have some warning for the limit exceeding for the strain or the displacement. And of course, the limit is something that the user can define. Okay, thank you, Professor Gellone. It's really late in the night in Italy, okay? So the last thing I want to show you, if I have still some second, is that we can not only perform real-time monitoring, but we can also post-process the data. We should be able to know. 5 seconds. Okay, sorry. That was, okay, so last 5 seconds, I would just like to thank the team, Demos team, and Fondazione Compagnia di San Paolo for funding the project. If you are interested, you can scan the QR code or visit our website. Thank you.
Thank you very much. Now, the team from Politecnico di Milano, okay, you're here. Good.
Okay, we can. Okay, I can start?
Yep.
Okay.
Hi everyone, I'm Jacopo Bardiani from Politecnico di Milano, and in this video I will show you how the inverse finite element method, also called IFM, can be used in real time to monitor the displacement of a railway beam bridge model. But what exactly is IFM? To answer that, we need a bit of context. Today, most bridges are monitored through manual inspections, which can detect early signs of damage, but are expensive and not continuous. A smarter approach is structural health monitoring, or SHM, where sensors are embedded in the structure to collect real-time data and support decision-making. One key aspect of SHM is shape sensing, also called deflection monitoring, since unexpected deformations can indicate structural issues. In recent years, a method called IFM has emerged as a powerful tool for real-time shape sensing. The inverse FEM is an algorithm based on finite elements and strain measurements. In the presented scheme, we can clearly see the main difference between IFM and traditional FEM. Unlike the classical FEM approach, IFM does not require knowledge of material properties or external loads. Instead, it uses strain measurements taken at discrete location as input to reconstruct the displacement field. IFM for slender beams is based on Euler-Bernoulli beam theory and works by minimizing a functional that quantifies the error between modeled and measured strains, where the strain field depends on the nodal displacements of the model. This functional includes 3 strain components: axial strain and bending strains in 2 orthogonal planes. The solution is the displacement field that minimizes the total error. As you can see, this method doesn't require material properties or external loads, only geometry and strain measurements. The experimental setup consists of several components. A railway track is supported by a 3 mm thick aluminum beam mounted on 3 columns that simulate bridge supports. The beam is instrumented with fiber Bragg grating optical fibers on its bottom side only, and strain data is acquired using an HBM unit via Catman software. To vary the load position and magnitude, a scaled electric locomotive with a trailer moves along the track, controlled by a potentiometer. Strain measurements are processed in real time by a MATLAB script running the IFM algorithm at around 50 Hz. The output is the vertical displacement field of the beam. Finally, a laser sensor placed at midspan on the right section provides reference displacement measurements for validation. A few more words are needed to better explain the sensing strategy and how it integrates with the inverse model. This diagram shows the sensor network layout and its deployment on the structure. An FBG system with the 32 measurement points was used, matching the inverse mesh with the 2 strain readings per element. Now, let's take a look at how the algorithm performs under different scenarios, both static and dynamic, to evaluate its effectiveness in realistic operating conditions. What we see on the screen is the IFM-based reconstruction of the vertical displacement field, obtained from real-time strain measurements. This final case highlights the real potential of IFM. Even under a fast-moving load, it can accurately reconstruct the displacement field in real time. Thank you all for your attention. If you're interested in testing this powerful technology on your own demonstrators or applications, feel free to reach out to us.
Okay, our next demo comes from Metis Design Corporation.
Ready to go. Hi everyone, I'm Dr. Sept Kessler from the Metis Design Corporation, and today I will be demonstrating our WISP system on a chip as applied to a representative Boeing 737 chemically milled fuselage panel. So what I have here is a dimensionally accurate fuselage section, including the chemically milled pocket depth. Along the edges of the chem mill pocket, we've machined a notch in order to create a flap, which is created to a reciprocating motor. And every time I push this button, it introduces 1,000 cycles to grow a fatigue crack from the notch tip. So adjacent to those notch tips, I have 2 carbon nanotube-based crack gauges in order to record the extension of the natural crack growth. And at the end of my bus, I have a WISP temperature and humidity sensor, which I'll also be recording at the same time. So before I came out here, back in Boston, we actually cycled this 10,000 times in order to initiate the crack. I didn't want to take the chance that the crack wouldn't develop in our 5-minute demonstration. So you probably saw when I first came up here, I clicked the collect button in order to see what the initial crack length was before we started growing the crack. I just put 1,000 cycles on there, and now let's see how long the crack has grown. So this is going to update the crack length, and then you'll also see in the header, it will update the temperature and the humidity, which is probably telling what you already know, which is cold and humid in here. So this chemically milled fracture fatigue problem was identified by some service-induced cracks that were found on Southwest airline flights. And subsequently, the FAA has issued a number of service bulletins and airworthiness directives requiring teardown inspection that can greatly impact operational availability on these planes. And this was pretty thoroughly reported at this conference 2 years ago by Danielle Stevens and Paul Swindell from the FAA. So this is truly an ideal application for structural health monitoring, where we're able to facilitate remote inspection without need for teardown, and be able to provide an economic, periodic inspection capability to trigger a manual inspection if something's found. So let's collect more data. You'll see as I'm collecting data, if you're close enough, little blue lights on each of the sensors as they're triggered. And now, let's start it up again. So to facilitate this test, I'm using a 3rd-generation WISP system on a chip. WISP is an ultra-lightweight, low-power digital twin companion tool. It uses a flexible distributed data acquisition architecture combined with edge processing capabilities. On each of our 10 by 10 millimeter chips that weigh less than 1 gram fully packaged, we have capability to take in inputs from both analog and digital sensors, in addition to having a local microprocessor that can embed algorithms to reduce data. We can daisy chain up to 64 of these over a 100-foot long bus, and we can collect data continuously or log on demand. We can mix and match sensors on the bus, including the list that I have there that we've already done for off-the-shelf sensors, in addition to some nano-engineered sensors like the crack gauge we have here. As for the crack gauge itself, the carbon nanotube gauge has trillions of carbon nanotubes that are laminated between a pair of thermoplastic layers to environmentally seal it. As a crack grows beneath the gauge, it physically tears the nanoelements apart, which permanently encodes this crack length as a change in resistance, even if no power is applied to the gauge. Recently, we conducted a detection sensitivity study using 60 aluminum beams, and we showed that we have the ability to detect reliably cracks as small as 1/3 of a millimeter. I tried timing each slide with this, but apparently I was fast on that slide. And you wouldn't expect the temperature or humidity to change just by like 0.1 or so. Oh. All right, well, lastly, we recently installed on 2 737s in collaboration with Delta Airlines. We have 12 crack gauges. It takes 10 seconds to collect data from the entire bus using a USB connection. Let's do that final crack. Thank you very much for your time.
All right, thank you very much. Our next group is Fatigue Pro Sensor and Sabahattin Zaim University.
Hello. Fatigue Pro is a startup developing a new type of progressive structural health monitoring sensor. The concept is very simple. It's very straightforward. It is a sensor with multiple fingers on it, and these fingers are notched. These have engineered notches. And with these engineered notches, we reduce the fatigue life. Okay, so it can be big like this, or it can be very small like this, depending on the application, obviously. The sensor is supposed to be made from the same material as the structure that you're working with. And all it's supposed to be, when you install, installation is important, obviously. So when you install, all fingers has to see the same load. So where do we install? Well, it's supposed to be installed in critical locations. Okay, critical locations, we know them. The designers know the critical locations, so we put them. When we put the sensor in those critical locations, sensors see the same fatigue load as the structure. And as a result of being having different fatigue life, fingers start breaking one by one in a progressive manner. This is where the name progressive sensor is coming from. Okay, so this is it's easy to understand how it works. I have a quasi-static model that we can see. I'm not going to demonstrate, not to lose my time, but the strain is different on each finger. Now, as the sensor goes through fatigue cycles, obviously the fingers start breaking one by one. Okay, starting with the one with the lowest lifetime. So typically the cracks are micro cracks. So micro cracks, detecting micro cracks is something difficult. It's not easy. So what we do, we use a nano paint, a special nano paint for detecting those cracks. For testing, we use this type of glass. We crack the glass with impact on a flat surface. So it's just like a stone hitting your windshield. So it makes a micro crack. And the nano paint can sense this micro crack very well. So the one on the right side that you see is actually, there is a crack underneath, and the nano paint can sense this thing very well, very reliably. Okay, so what do we do? Okay, initially we start with this, then we cover it with an insulating layer. After we completely insulate, and then we put our conductive nano paint, and then the whole thing is supposed to be obviously covered with a special coating to protect everything, and at the end it becomes something like this. So this is the final form of the sensor. Now, after this, well, what do we do? Well, the nano paint, by the way, is something is very good for detecting cracks on intricate 3D objects. For example, for this thing, you have the welds, and it's an intricate shape. So when it's applied, it can sense the crack on the object. Well, it can be also used for measuring the crack growth. Okay, so how do we collect the data? Well, this is the sensor. Now, how do we collect the data? To collect the data, we use an interesting method. This is our demo. I have our demo. This is a mock-up sensor. We are simulating the breakage of the fingers. The important thing is that the information is transmitted with a 2-wire, only 2 wires. And this thing is completely passive. It's 0 power consumption. Okay, so with this, we transfer information reliably. This is available, then you can, if you want to see it, you can test it yourself. It's a pure resistive network, so you can put it in harsh environments without any problem. And it can reliably tell you the levels in all cases. Now, after we get the information, how do we transmit this information to outside? Well, for this, we have 2 different methods. One of them is obviously the NFC, RFID. It can reliably send information about number of fingers breaking, condition. Or, and this is, by the way, it's excellent for crack detection and monitoring, so with nanopaint, and it's actually very successful.
Time is up.
Sorry for that. Okay, so we use LoRa for transmission, and if this is a live application that you can see, and the live sensors. These are applications. So in case if internet is not available, we have a satellite modem. This is, you can put it on somewhere that sees the sky, and it can relay the information through the thing. Thank you very much.
So the next should be National Research Council of Canada, but are they here? I didn't. Okay, so they are not here, so we go to the next, which is Structures and Composite Lab and Asylum Technologies. So we have people from Stanford. Not you, your colleague. Yeah, I think they're coming in with all the stuff.
It's big enough. Nice model. So NRC wasn't here?
No.
Okay, well, gives us a few extra minutes.
No. If they accepted the proposal from our president, they would not be boarded.
In fact, they can't stay.
You know, people are scared because if the person who is supposed to present origin of some of the countries that cannot transmit it, there is.
Yeah.
Why is it?
No, absolutely. Yeah. Yeah, these are strange times. This is nice. Really making the effort.
Ryan, should I start? It's here. Yeah. I'm ready.
Okay.
Hello, and welcome to IWSHM 2025 today. Thank you for joining us. We would like to present our project Fly by Feel under the guidance of Professor Foucault Chang and in collaboration with Excellent Technologies today. So we have brought an aircraft here, and if you can see, we have mounted a sensor network to its right wing. This sensor network is composed of PZT, strain gauge, and RTD sensors. We would like to give you a short live demo that this sensor network can feel the vibration and the strain when the wing is bent. So let us proceed. This is our live dashboard. On your right-hand side, you can see PZT signals, and on your left-hand side, you can see strain gauge signals. So Brian will now tap on the wing, which will make the PZT signals excite. So if we now start bending the wing upwards or downwards, and you take a look at the left-hand plot, you will see the strain gauge signals change their results. Exactly. So traditionally, SHM applications enhance safety by monitoring the health of a structure. But what if we could not only monitor the health of this wing, but also feel the airflow around it. So with this fan, we would like to demonstrate this aircraft flying through the air, and a free airstream will hit this wing right here. So we will now turn on the fan. On the left bottom screen, you can see live data from the avionics of the aircraft. So you can see an indicated airspeed and dynamic and static pressure. As you can see, our PZTs have been excited, and our strain gauges have also recognized that the wing has been deflected in this free airstream. But we want to take this one step further. Here's where the real magic comes into play. We have trained a machine learning model that is capable of taking all this sensor network data and actually fly this aircraft. We call this model iFlyNet. So our edge AI computation is done right here in front in our payload bay, which we can also unveil. Do you want to just, okay. Okay. All right. This is our custom designed payload bay, which has never been done so before. In the following, we would like to show you a simulation where our iFlyNet model infers real aerodynamic parameters based upon wind tunnel test data.
Thank you, Louis. So far you've seen real-time data acquisition from the sensor network as well as the airplane, and everything is synced. So in this video, we will show you a simulation from the data that we captured earlier. We haven't got a chance to fly this, but this is coming from a wind tunnel data. And yes, if you apply this, Louis, basically we fed the data to our iFlyNet model, and we imitate how avians, how birds sense the flight environment. So as you can see at the bottom plots, all flight metrics are predicted very closely to the actual wind tunnel values. And this is the first such a system works this way. And even stall, when the angle of attack is increased, lift drops, our model very precisely predicts. And also across different flight states, different airspeed, different angle of attack conditions, our model does a very good job in tracking the real aerodynamics. So in the end, with fly-by-feel, we take the SHM, which is designed to enhance flight safety, and open a new paradigm for flight state awareness. So that's it. Thank you very much, everyone.
Excellent. Thank you very much. The next group is Hong Kong Polytechnic University. So far, it went very smoothly. If we keep up this pace, we'll be ahead of time.
I'm actually surprised because in the past years people who got accelerate measures so try to remove them from the stage.
It would look. It's very disciplined. So this should not take too long, I hope. So when did you move over to the United States?
2009.
Okay, a while ago. Yeah. You never regretted it?
Until year 2025. No.
Okay. Are you worried about your job?
I'm worried. The things are not. I mean, I'm originally from Serbia, and I saw this happening there in the 90s.
Yeah.
I mean, same pattern, same. In a sense, you say, okay, that was a country that was, previously non-democratic, it was socialist. It was very free communist country, but it's not, you have working practices and everything. And the thing evolved in the wrong way. So that's why you would not expect that this happens. But every day, this morning, we sent people in EU to tell them that they should not follow climate ideology. Not use eolian and solar, but they should buy.
Hello, everyone. Sorry for the trouble. My name is Zhongqun Su from Hong Kong. I'm not supposed to be here in this session. I'm on the stage. That is simply because my colleague, Professor Yongxia, who is also the PI of this structural health monitor system, I would like to showcase in front of you. His flight has been rerouted. So due to some small incident yesterday, so he has to fly across the whole world, all the way from London back to Hong Kong and then come to San Francisco. So his flight is expected to touch down at 6 p.m. today. So if he is lucky enough, he will be able to catch today's banquet. But anyway, I'm just take his job to introduce the system he and his team developed. So the system we would like to showcase in front of you, that is one food bridge digital twin structure health monitoring system. So let me introduce the team member first, because this is a system developed by Professor Yongxia and his team. So please bear with me. So I just get myself familiar with the whole system just before the lunchtime. Okay, so let me quickly introduce the system he and his team developed. So that is one food bridge. So that is a couple years ago, our university decided to develop a small food bridge to link two campuses in the downtown area in Hong Kong. So that is probably talking about 80-something meter long. And so at that time, our university encouraged all the faculty members and tried to make use of this food bridge as a test bed to deploy their new technologies. So Professor Yongxia was one of them. He received generous support, about probably 2 million Hong Kong dollars, that is equivalent to 250K US dollars, to develop the whole structure health monitor system installed and embedded in this food bridge. So he instructed me to show you two videos. One is talking about the design of this bridge. So sorry, so there's no audio. So anyway, so this footbridge design was inspired by so-called the elegant leaping fish. Anyway, so that is like this shape. So we directly jump to the construction. So here. So that is during the construction of the footbridge, Professor Yongxia and his team developed this structural health monitoring system and embedded during the construction stage into the footbridge. So he installed their team. They used different kinds of sensor. So that is mainly, so that is the whole system. Bear with me. So I'm not see this website much earlier than you. They have, look at the sensor, how many sensors they use. So they use the strain gauge, they use optical fiber, they use accelerometer. So that is altogether. So they got 10 types of sensor, altogether 77 in together. And so they measure the wind speed, anemometer, accelerometer, and also strain gauge. They put the sensor on different position of the footbridge. So they developed the data acquisition and the transmission module and collect the data and send the data to the central control. So one thing I would like to draw your attention is this is not any software, it's not app, it's just a website. So you can directly input this website address, and then you can real-time to monitor all those data captured by this sensor in the real-way manner. For example, you can monitor the vibration. Yeah, you can monitor vibration. So if you look at the time, so that is now is today. Yeah, that is 11th September in Hong Kong. That is 7:45 a.m. in the morning. And also you can monitor how many person working on the bridge, and also the displacement. Displacement is along 3 dimensions. And with that, so then using the digital twin, based on this information collected from this sensor, so we can show the people, you can see people working on the bridge. Trust me, probably our president used this data to monitor how many people working on the weekend. And then you can monitor the vibration. So look at that. So you see the vibration. All this data are real time. So that is in conclusion. So Professor Xia and his team developed this structural health monitoring system for the footbridge using digital twin technology, real time monitor the health status for the bridge. Okay, thank you very much. I hope I make it clear.
Yeah. And now we have excellent technologies.
Okay, we all set? Hello, everyone. I'm here representing Acelent Technologies, and today we're going to be demonstrating our SHM system designed for inflatable space habitats. So by way of introduction, we have a quick video. No sound. Can you? Did
you select the headphones?
I did. It should be decimator?
No, headphones.
No, headphones. Okay. Headphones.
That's it.
Okay.
As space missions stretch to longer durations and farther horizons, there is increasing demand for structures that provide the maximum amount of livable volume with the minimum amount of mass. Inflatable structures can be deployed as living spaces in orbit and on surface exploration missions. Space agencies are aggressively pursuing inflatable structures as candidates for long-term habitats in space and on the surfaces of the Moon and Mars. Inflatable habitats are truly remarkable structures that have allowed us to extend the length of time that humans can spend living and working in outer space. A critical factor in the use of soft goods technologies for space habitats is the ability to monitor and assess the structural health of an inflatable module, especially in the presence of threats from micrometeoroids and orbital debris. Fortunately, Acelent has an innovative solution. We have developed state-of-the-art sensor packages containing PZT transducers and strain gauges that are easily integrated with the Vectran straps that are used to manufacture an inflatable habitat. Our sensors are sensitive enough to detect impact events while being robust enough to survive in harsh environments. Testing shows they can withstand the strain of inflation yet have minimal impact on the performance of the inflatable structure. Not only are these sensors easy to install, they are part of an intuitive system designed to monitor the entire inflatable structure. Acelent's structural health monitoring, or SHM systems and enabling technologies play a crucial role in shaping the trajectory of future space exploration, as well as numerous other industries. Acelent. Smarter structures for a safer world.
So as you can see in the video, this inflatable habitat, of which this is a subscale model, because these are designed for humans to live and work in space, whether that's on orbit, on the Moon, exploring Mars, or beyond, this subscale version has our sensors installed. So it's made out of a series of Vectran straps that compose a webbing. So you have your axial straps and your hoop straps, and these bear the load as this structure is inflated. Now, we unfortunately couldn't inflate it live here to show you because of safety concerns, so we have the inflation shown in the video. But what we are going to show is once it's inflated, we can use our sensors to detect impacts at specific locations on the structure. So this is going to represent like a micrometeorite impact on orbit. So my colleague Ontario is going to be the micrometeorite, and he's going to show you the impact detection as soon as I enable it. There we go.
Impact detected at X coordinate 7.6 inches and Y coordinate 18.3 inches. Impact detected at X coordinate 16.7 inches and Y coordinate 5.6 inches.
Of the impact. So each place that he hit detected the impact in 2 different locations. We also estimate the force level of the impact so that the operators or the astronauts or the ground crew know exactly how severe the impact is and whether there's any risk of damage to the structure. And one last thing, if I have the time, is I want to show some preliminary testing that we did to verify the integrity of the sensors and the durability on these straps. So this is a test where we are pulling the Vectran strap with our sensors installed to failure. And we're looking to see that the sensors survive and also that they don't reduce the durability or the survivability of the Vectran material. So to our knowledge, this is the very first time that anyone has ever installed sensors that have survived on a soft goods inflatable material and are able to accurately detect strain, load, and impacts. Any questions?
I think they're out, yeah.
All right.
The University of New Mexico. Yes, you're on. All right, excellent. Do you need a handle? Oh, yeah. Please go on. Oh, thanks.
Do they stop it?
Number 1 or number 2? How many do you need? 2. You need 2. That's going to be number 2. Okay. And then number 1 has to come over here.
It doesn't make it this far?
The other one cannot reach that far, so this is as far as it can reach. Do you need audio in this computer?
What's that?
Do you need audio from the computer? You would have videos that have audio. No audio on either computer. This here is 1. That's 2. Who's speaking?
Since they're preparing, just a quick announcement. So here's the updated bus schedule. You can pick up a hard copy over here when it's
You
done.
want a second mic?
And also you can also look up on the website. It's also updated. We should have enough bus for everyone, so we can wait until the SHM inaction to be over and then head to the bus area. So like I know, like I received a lot of concerns saying that it's ending at 6, but the bus leaving at 6. But we have multiple buses that will cover everyone. So just want to assure that, and then you can also pick up the schedule here. 6 and 1. So we have 7 buses running. The earliest one is leaving at 5:55, and the other one at 6:05, 6:10, and 6:20.
Can you hold the mic for us because we need our hands?
Yes.
Oh,
Oh yeah, it's at the normal bus stop at the entrance to Marsh.
I need help. Let me see who can help me.
I want to
help.
Yeah, sorry.
Let me see who can help. This is deck 1. This is computer 1. That's computer 2. Tell us what you want us to take. What do you want first? You're participating? You're participating? Okay. Let me see. I need someone to help. Hadi, can you help us? Holding the mic. Come here. Yeah. Can you hear me? Yes. Okay. So we're getting ready here, and while we get ready, because on the HoloLens we use the 2 hands, I'm going to help my good friend Hadi to be the mic stand. So I think you're going to move it for me. If Masa needs, you can move it. So right now I can hold it, but then my name is Fernando Moro, and I think, can we see the streaming is working? And I'm leading this group of smart people. We call ourselves the Smart Management of Infrastructure Laboratory. And we believe the international workshop of SHM is going to change today. We're going to bring the machine to work with the human to be smart, humans and machines working together. So what we believe is that humans are good people. They work very hard for the future of infrastructure. And I worked 10 years in industry and identified that the inspection from cradle to grave is the core of SHM. The inspection from cradle to grave is to repair the health at the baby stage, okay? My student, Masa Sanae, takes this to heart. We like to help the humans because they are experienced and they have the context of the work site, but their information may be subjective, can be time-consuming, and at times, many times, is unsafe. You told me you hurt yourself when you were working with River. So you get your hands with some scratches. It happened to me. It will happen to you. So we're going to think like Masa does. Let's help comparing the design drawings with the shop drawings at the site with the machine. You will have a permanent record of the structure forever. So there is a crack 20 years later. You will see where the river was before. Another thing that we are thinking on doing is to show you what she's actually working on. So we're going to have the display on Masa Sanae. Masa Sanae is a PhD student at the University of New Mexico. And can you use your hands or you want me to hold the mic?
Thank you, Dr. Moreau. So what we're doing for inspection of rebar in traditional method is that we use the tape measure. So we need to go bar by bar and check the spacing of the bars. So we developed an application in augmented reality where we overlaid the as-built model on the design drawings, and we overlay that on the actual rebar. So you will see all those bars that are red, they need to be moved. So I want Dr. Moreau to help me with the robot to move rebar number 2 because I'm not happy with this.
Thank you very much. What I'm going to do is work with my team on machine-human collaboration. And what we're going to have is to show how this works. So I need to work with my team, and I'm going to verbally communicate with them, so you're going to follow how this really works. If they approve, I will open the app. Is it good to go? I'm going to be very fast to anchor the coordinates. If they like it, we are lucky. Good? Yep. Okay. So when he tells me I can show you, I can do my thing. Can I go?
Yep, go ahead.
All right. So I'm going to open the app here, and I'm going to move it this way. It was developed just for IWSHM. And now the first thing is the, let's see if they can see this. I'm going to ask the machine-human people to approve the robot intervention. The robot intervention needs to be anchored on the space. And they will approve for me. They will approve for me their position, and if they give me the green light, I can go for the anchoring.
Looks good.
Okay, I'm lucky today. And then here I will put the reference to indicate a 90 degrees repair, or I guess health repair or health intervention. If they like it, we are very lucky.
Yeah, looks good.
Okay. They are nice with me today. Same position, can I?
Yep, go ahead.
All right. I send. I don't know if it took it.
Can we go ahead and change the screen? Change screens. Looks good. Looks good.
I'm going to tell the robot to move, and we're going to see if it does the activity that was designed for. And then I think, I don't know, you can see the handler is going to close it and move half an inch for engineer Sané. Can you do it? I think what we need to do is just to believe that this is happening. Thank you very much. Okay, great. So what we believe is that the future starts today. Thank you for joining IWSHM. We didn't introduce ourselves, so let's do it now. Fernando, yours truly.
Mahsa Sané.
Ronan Reza. Michael Carl.
Have a good night.
Thank y'all.
Okay, and our next group is from Rensselaer Polytechnic Institute, and they are getting